Human errors. Even when they have the best intentions, humans are known to be unreliable. For example, one study of large internet services found that configuration errors by operators were the leading cause of outages, whereas hardware faults, servers, or network played a role in only 10 to 25% of outages. So a hardware and network actually play 25%, while the human error are 75%. How do we make our systems reliable in spite of unreliable humans? The best systems combine several approaches. First, design systems in a way that minimizes opportunities for error. For example, well-designed abstractions, APIs, admin interfaces make it easy to do the right thing and discourage the wrong thing. So it's interconnected to the software. You need to create abstractions with the API, unit test, an admin interface. It also related to using outside tools to track anything that will abstract or gain better understanding on the system, such as the dashboard statistics for login requests, read and write requests, etc. Also, by applying design principles that match the user or your user mental model. However, if the interfaces are too restrictive, people will work around them, negating their benefit. So, this is a tricky balance to get right. Decouple the places where people make the most mistakes from the places where they can cause failures. In particular, provide fully featured non-production sandbox environments where people can explore and experiment safely using real data without affecting real users. So, when you're developing, make sure you have a copy of the repository, and also it's organized in a way that a lot of developers can work to your project at the same time. So that's how you can minimize human error. Additionally, aside from copying repository, you can also copy the exact folder. You can transfer that via USB and then use third-party tools that allows you to simulate that data. What I would add with this is that it's also useful to have a better understanding or a dashboard of the features on your web app that the customer usually use, because that will allows you to decouple that main feature from the rarely used functions such as the one in menus. Test thoroughly at all levels, from unit test to system integration test and manual test. Automated testing is widely used, well understood, and especially valuable for covering corner cases that rarely arise in normal operation. Allow quick and easy recovery from human errors to minimize the impact in the case of a failure. For example, make it fast to roll back configuration changes. Roll out new code gradually so that any unexpected bugs affects only a small subset of users. So this is the real how the real world push code. They usually just change, especially for big tech, because they are specialized. They only push a certain number of changes on the code to avoid this big inter a bug in this interconnected software. Also, they also change small step at a time so they can roll back changes. They also they prepare in case their system fail, such as the push that to GitHub. So they have a GitHub repository They take note of the dates that the system works and just basically roll back on that instance. Or in other cases, if the system is big, they provide a lot of instance, and then there is a base image, kind of like where the system will fall off in case there is a bug, or it causes an outage on entire application. So every modern big app experience this every day. This downtime, they just minimize the consequences. Implement good management practices. Additionally, with admin interfaces, so whenever you're designing an app, make sure you include that into the design. Another interface for admin, another interface for dashboard, because that's actually will allow you to be more scalable long term. Not just creating an app, a full stack app, without having those user roles. It may be complicated for configuration, but it also allows you to scale, because that's actually how Twitter or big tech scale. They actually use multiple services in the cloud, such as EKS for streaming, DynamoDB, etc. And those, even the simple thing to avoid those, the overloading, actually helps them avoid those significant consequences of serving multiple or huge user base. Scalability. One common reason for degradation is increased load. Perhaps the system has grown from 10,000 concurrent users to 100,000 concurrent users. Scalability is the term we use to describe a system's ability to cope with increased load. Note, however, that it is not a one-dimensional label that we can attach to a system. It is meaningless to say X is scalable or Y doesn't scale. Rather, discussing scalability means considering questions like, if the system grows in a particular way, what are our options for coping with the growth, and how can we add computing resources to handle the additional load? So we will, just saying that X is more scalable than Y doesn't really provide us the details, or it makes it simpler than the reality, which makes it false, because in actuality, some parts of that system, that Y system, is more scalable than X, and some part of the X is more scalable than Y. Now, to be able to scale, you need to first understand your load. Describing load. First, we need to succinctly describe the current load on the system. Only then we can discuss growth questions. Load can be described with a few numbers, which we call load parameters. The best choice of parameters depend on the architecture of your system. It may be requests per second to a web server, the ratio of reads to writes in a database, the numbers of simultaneously active users in a chat room, the hit rate on a cache. So even the hit rate on a cache, the previous example we saw, actually check the cache first before it write to the actual database, because writing to the actual database costs a lot of computes or something else. So as you can see, there's a lot of factors, including the cache, the simultaneous users or the concurrency, the ratio of reads to writes, requests per second, or something else. Perhaps the average case is what matters for you, or perhaps your bottleneck is dominated by a small number of extreme cases. So sometimes the bottleneck is the extreme cases, especially if you are in a queue. That's actually called tail head latency, which one process makes all the other process slower because of that one process. So you may encounter that as well. Example is Twitter. Two of Twitter's main operations are: first, post tweet A, user can publish a new message. So if you are just a startup or you're just doing your thesis, this really doesn't apply. But when you, it's worth it to understand this, because then you will appreciate that what you, if you're able to make a full stack without actually worrying about this thing, you will and then you know this before actually encountering this in your real web application, you are actually more prepared to handle those edge cases. So for example, for Twitter, uh, two of Twitter's main operations are post Twitter A. Post tweet A, user can publish a new message to their followers. 4.6 thousand requests per second on average. Over 12,000 requests per second at each at peak. So that's the worst case scenario. Second, home timeline. A user can view tweets posted by the people they follow. 300,000 requests per second. So this home timeline actually, first Twitter actually read that post in each of the followed people. So you can imagine 300, that's the reason why it's 300,000 per second, because at a given followee, you have on average of 75 followers, or 75 person you follow. So that 75 person, you need to read each one of them and then merge them, of course, into one timeline. That's actually how timeline are made. So simply handling 12,000 writes per second, the peak rate for posting tweets, would be fairly easy. However, Twitter's scaling challenge is not primarily due to tweet volume, but due to fan out fan out each user follows many people. Fan out liar, or fan out, just fan out. Basically, each user follows many people, and each user is followed by many people. So that's kind of many to many. There are broadly two ways of implementing these two operations. First, posting tweets simply inserts the new tweet into a global collection of tweets. When a user requests their home timeline, they look up all the people they follow, then after that find all the tweets for each of those users. So this is what I meant by getting, or when a user requests a timeline, they look up. So instead of get, they look up the people they followed and then check the latest post and then merge that into one. Then after that, find all the tweets for each of those users, then merge them sorted by time. In a relational database like in figure 1.2, you could write a query such as this. So this is actually how you do that. So it's let's say you directly request or look up each request for each of the follower of the user. This is what you do. So it's one global database. So select tweets, users from tweets. The next line, join users on tweets.sender underscore id equal users under dot id. Next line, join follows on follows that followee underscore id equal users dot id. Next time, where follows that follower underscore id equal current underscore user. Second, we can maintain a cache for each user's home timeline, like a mailbox of tweets for each recipient user, like this here. So when a user posts a tweet, it look up all the people who follow that user. So instead of Instead of the user having the burden of reading or looking up the tweet, the the poster or the influencer that actually uh, tweeted will write it in a cache in advance, so that when the user requests it, it is nearer to her. You will apply a CDN as well, and you can easily read that because uh, like the the request we have for write, we don't have as much bottleneck for publishing message to their followers. We only have 4.6 thousand, unlike the read request from the user, which is 300,000. So if we have 4.6 thousand writes per seconds, that's easy because uh, it's lower than 300,000. Imagine 300,000 and then multiply that with the number of the follower that each user are following, then you get this bottleneck, or you hit your peak in scaling. So then insert the new tweet into each of their home timeline caches. Now, instead of the client or the user having the burden of looking up, the influencer are actually the one inserting it into their home timeline caches. The request to read the home timeline is then cheap because its result has been computed ahead of time. So it's an example. Current login user 1.70. So we have users table, tweet table. So this is how we apply that in a simple relational schema for implementing a Twitter home timeline. You put that in a cache. So this user login is the influencer. So this is the tweet, just setting up. And then the timestamp, and then you put that to the user's cache, or to its followees cache, which is an ID of 12 and name jock and profile 1.23 per etc. JPG. Figure 1.3, Twitter's data pipeline for delivering tweets to followers with load parameters as of November 12. So as you can see, these are the user posts, or the influencer that this is the its tweets, and it posts it into the user timeline, and then the user now just requests its timeline. So this is what fan out means. Fan out delivered tweet to each follower up to 31 million followers per user. So we optimize for writing instead of read because it's more expensive to read. Also, we also have some user that will have a delay response from that, you would imagine, because if you have a 300,000 read and you implement the previous version of Twitter's algorithm or architecture, therefore some user will take like forever to load their to look up the tweet because of just the nature of the hardware and the tail latency event, which we will discuss later. Now, the first version of Twitter used Approach 1, but the system struggled to keep up with the load of home timeline queries. So the company switched to Approach 2, which is creating an, optimizing for write to the cache near the user, or to the user home timeline, cache to the user home timeline. Therefore, the user just needs to request for its own timeline. So this works better because the average rate of published tweets is almost 2 orders of magnitude lower than the rate of home timeline reads. Actually, it's not 2 orders. So maybe that means like 100 times magnitude, because as you can see, 300,000 and 4,000 is 100, almost 100 times difference, magnitude in difference. So in this case, it's preferable to do more work at runtime and less at read time. So, what sentence means it's preferable to do work at runtime and less at read time? Process tweets fan out when someone posts so that reading the home timeline becomes extremely cheap. This approach is sometimes called fan out on write. So whenever we're optimizing for write, that's what we call fan out on write. Whenever we're optimizing for reads, that's what we call fan out on read. So why more work at write time makes sense even if reads are 100x higher? Reads loading home timeline are much more frequent than writes posting a tweet. So naturally you ask, shouldn't we optimize read time because that's the dominant load? The trick, optimizing read time is best if and only if the read time computation is cheap. But in Twitter's case, read time computation is very expensive. Let's compare the two strategies. Strategy 1, fan out on read. Do minimal work on write, do heavy work on read. Write equals simple insert, read equal expensive. Fetch every followed user, fetch all tweets for each user, merge sort by timestamp, possibly join with user profile data, possibly paginate. Problem, if a user follows 1000 accounts, reading about their timeline means merging tweets from 1000 sources. Not just that, you also have to request different services attached to it, such as the ads. You also need to paginate it, the profile data. You also need to merge sort. You also need to fetch all tweets for each user. You also need the sorting service, etc. Multiply that by millions of users reading thousands of times per day. Reading becomes unbelievably expensive. Twitter actually tried this first and it broke. Strategy 2, fan out on write. Do more work on write. Read becomes trivial. When A posts a tweet, push that tweet into the timeline cache for each follower, i.e. 1000 followers to 1000 pushes. Now, a user reading their timeline just reads a stored list, cache, pre-sorted, already assembled, no merging, no heavy database joins. Result, reads become extremely cheap, basically a simple key lookup. And this matters because writes happen maybe 6,000 times per second. Reads can be 300,000 plus times per second. So even if pushing to followers is expensive, the cost of expensive read operation would be much worse. So in comparison to read, it is much worse. The math example Twitter used from Twitter's 2012 paper, tweets is 4,000 tweets per second. Timeline reads 300,000 read per second. Reads are 75x more frequent. If you make read expensive, you multiply pin by 300,000 per second. But if you make writes expensive, you multiply pin by 4,000 per second. Therefore, better to make write expensive than to make read expensive, 75x more often. This is exactly what the sentence means. Intuition, you optimize the thing with higher total cost, not higher frequency. Even though writes are fewer, if each read is expensive, it dominates total CPU load. So instead, make write heavier, total write cost equal manageable. Make read ultra light, total read cost equals more per op times huge volume. This is classic pre-computation or materialized view thinking. Why your intuition about 80% load should get 80% optimization is close but incomplete? Yes, reads dominate the load. But strategy 1, read equals super expensive. Strategy 2, read ultra cheap. Thus, optimizing the read path gives the biggest system-wide win. The only way to optimize reads is pre-compute results at runtime, do more work at runtime. That's why. Summary, the key idea. Twitter's writes are relatively cheap in volume. Twitter's reads are massive in volume. Therefore, you want reads to be as cheap as possible. The only way to make reads cheap is to pre-compute timeline contents. Pre-computation, pre-computation happens at runtime. Therefore, do more work at write time and less at read time. However, the downsides of approach 2 is that posting a tweet now requires a lot of extra work. On average, a tweet is delivered to about 75 followers. So 4.6 thousand tweets per second become 345,000 writes per second to the home timeline caches. But compare that to 300,000 times the number of something, it will be much more. But this average hides the fact that the number of followers per user varies widely. And some users have over 30 million followers. So actually those second strategy is not entirely the implementation of Twitter now. They actually use hybrid. There is also an advantage on using the strategy 1, which is putting that in a global database and making the user request it. Doing this in a timely manner, Twitter tries to deliver tweets to followers within 5 seconds is a significant challenge. In the example of Twitter, the distribution of followers per user may be weighted by how often the user's tweet is a keyload parameter for discussing scalability, since it determines the fan out load. Your application may have very different characteristics, but you can apply similar principles to reasoning about its load. The final twist of the Twitter anecdote, now that approach 2 is robustly implemented, Twitter is moving to a hybrid of both approaches. Most users' tweet continue to be fan out to home timelines as the time when they are posted, but a small number of users with very large number of followers, i.e. celebrities, are accepted from this fan out. Tweets from any celebrities that a user may follow are fetched separately and merged with that user's home timeline when it's read, like in approach 1. This hybrid approach is able to deliver consistently good performance. Second, so we were now able to define load and the nuances on how you can actually optimize that in real world. In the future videos, we will discuss how we actually deploy that, or what does it actually look like in real world. Now, describing performance. After we describe the load, we need to describe its performance. How do we describe the load performance? Once you have described the load on your system, you can investigate what happens when the load increases. You can look at it in two ways. When you increase a load parameter and keep the system resources, CPU, memory, network bandwidth, etc. unchanged, how is the performance of your system affected? And then, when you increase a load parameter, how much do you need to increase the resources if you want to keep performance unchanged? So, in a real world example, usually if the CPU of your instance, for example, your app instance where your front and back end are deployed, so of course it has an OS for app services, for example in Azure, you check if the load is greater than 75%. You can actually automate the scaling or replication of your instance if it increases 75%. So those are the one of another view of describing this performance, but as we will see, it is more nuanced than that. So in a batch processing system such as Hadoop, we usually care about throughput, the number of records we can process per second, or the total time it takes to run a job on a dataset of a certain size. In online systems, what usually more important is the service response time. That is the time between a client sending a request and receiving a response. In an ideal world, the running time of a batch job is the size of the dataset divided by the throughput. In practice, the running time is often longer due to skew, data not being spread evenly across worker processes, and needing to wait for the slowest task to complete. Latency and response time. Latency and response time are often used synonymously. but they are not the same. The response time is what the client sees. Besides the actual time to process the request, the service time. It includes network delays and queuing delays. Latency is the duration that a request is waiting to be handled, during which it is latent, awaiting service. So we will discuss this in the future video.